All right, let's get started. Good evening, everyone. I am Sushil. Nice to meet you all. And since Dr. Redkar is traveling today, I'm covering a guest lecture for today. Um, and I'm a postdoctoral researcher working with Dr. Redkar in his lab. But that being said, I have no part in the class, in this class for the grading perspective or any of the homeworks or assignments. Uh, but any doubts or concerns you have with respect to today's lecture, you could always post it on the comment section and we can discuss about it. Um, that being said, today's lecture is gonna be on a topic called trajectory generation. Let me start sharing my screen. Just want to make sure if, yeah, make sure it's my, all right. So I guess you all can see in my screen. So today's topic that we're going to talk about briefly is trajectory generation for a serial manipulator. And the idea of this lecture is not for you to learn everything about trajectory generation. It itself is a big comprehensive topic. People do dissertation and like an entire research on different optimization techniques, different methods uh, to generate a trajectory, the optimized trajectory for any serial manipulator. But in this lecture, what I'm going to do is give you a brief overview or like kind of introduce you to how some of the things are done in case of what is trajectory generation, what is path planning all about, and um, is how it all gets started. So I guess I have muted you all, but in case you have any doubts or any concerns, feel free to drop your questions in the comment section, in the chat window, and we will answer them uh, as possible, as much as possible in this class section. So when it comes to trajectory generation, the the key thing that the two terminology that is played around in robotic systems is path and trajectory planning. Um, yeah, you can use the part of this in your assignment, but I'm not sure um, to what extent of trajectory planning or trajectory uh, um, or the trajectory planning is requested in your assignments so far. So I'm not sure about the assignment aspect as to if this is required or not. That is something that you guys might have to check with Dr. Redkar. But as of now, um, I think you guys are supposed to go into the part of Lagrangian dynamics and understand the dynamics of the robotic systems. But this is something which is which goes in line with the dynamics of the robotics, and it's not essentially a requirement for understanding the dynamics, but it is something that you would like to have for practical applications in your real world. So the two things that, as I was saying, is being used very frequently is path and trajectory in robotic systems. And what they together give you is how you would like to have your robotic manipulator and effector move from one location to another. and it can be for multiple applications. It can be with respect to the pick and place manipulator. It can be with respect to any of the other systems where you would need to design the manipulator to move it in a particular fashion or in a particular manner, in a particular path, is what it is all about. The science or the mechanics which is behind all this is all included in trajectory planning and generation. So what when we look at motions, it is like a sequence of events that happens, and to make that sequence of events happening, or the sequence of motions to happen, there are two aspects of it. It has both kinematics and dynamics of the robotics playing in together for the trajectory generation. So we cannot just rely on just one aspect of it and then design the manipulator. You need both aspects of it to understand or to plan a path or a trajectory very well in case of trajectory generation. So that being said, let me first clarify what is the difference between the path and trajectory. Some of you guys might have used this in any of your some of your other classes, but what path consists of just the sequence of robot configuration in an order, which means that it is like you are setting different destinations, or like a destination and different points on your Google Maps, right? You are just giving the address, and that is what is deciding the path. So if for example, if you want to go from airport to Mesa, you enter a final destination as Mesa from your Phoenix airport. But if you decide that you would like to go via the Tempe campus, so then the Tempe campus is another point in the path that you are adding. And the path that it shows, that is from Phoenix to Tempe campus and from Tempe campus to Mesa, is just the path. Now, when it comes to trajectory, there are uh, there are multiple ways of going about this path. So when you say the path, you just mention the 3 points, and you say that this is the starting point and this is the ending point, and B is going to be the intermediate point. Now you are not specifying in a path that if you want to go to A to B, or like from first point to the intermediate point in 15 minutes, or you want to end up in 1 hour, or you want to finish it in 2 days, you are not adding a time aspect to it. So when you add a time aspect to it, you decide the trajectory. So when you try to use Google Maps, you get multiple options, and the option that you select, say if you select something which says shortest time, or the fastest time that you would like to reach, that is specifying the trajectory for your travel. So similarly, when you use robotic manipulators, you could give the 2 points in space, that is in 3 dimensions, and you could specify that, okay, these are the multiple points that I would like to have my manipulator end effector pass through. But once you specify the time aspect to it, it becomes a trajectory specifying how fast do you need from A to B, from B to C, or how like at what velocity would you like to get at point B, and what acceleration rate can it take from between A and B, things like that. So when there is a time perspective coming into picture, that is trajectory. So that is like the main distinction that I want you guys to understand from this particular lecture, that path only mentions the three-dimensional point in case of a manipulator. Trajectory actually gives how you go about those points in time, right? So it's like a space-time variable, whereas in path, it is just the space aspect as the variable. Now, In case of serial manipulator, there are two ways of going about this. If you want the end effector going from point A to point B, you can do two different ways. One, you could specify it in joint space. So when you say joint space description, you give the joint angles or the joint variable if it's a linear displacement or a translational element, then you give the joint variable um, and ask the manipulator, okay, for from this point A, keep the theta 1 angle as 0, theta 2 angle as 30, theta 3 angle as 45, and then gradually keep increasing theta 1, theta 2, theta 3 in increments of 5, 10, and 20 degrees respectively. And then you say that, okay, whatever happens after 5 increments or 10 increments is what the endpoint is. And when you do this, you give your constraints only in the joint space where you mention only the joint variables, and which is quite convenient, right? Like when you have the like the manipulator design, and you have the forward kinematics all decided, then you can just keep changing, playing with the angles, the joint variables, and then you can know, okay, what is going to be the final point, or what is going to be the three-dimensional point corresponding three-dimensional point in X, Y, Z coordinates using the forward transformation, the forward kinematics. So you give the joint variables that is entirely in joint space. The other aspect is doing the Cartesian space description. That means you don't care what kind of manipulator you are using. You don't care about the three, if it's a 2 degree of freedom manipulator, it's a 3 degree of freedom manipulator, if it is having a revolute and a prismatic joint, or if it is having two revolute joint, what your final requirement is the end effector to reach from point A to point B in a straight line, or it needs to move from point A to point B in a three-dimensional space. So one way of going about this is you have a point in 3 dimension which has x, y, z coordinates. You do the inverse kinematics, find the joint variables corresponding to that point at point A, and correspondingly, you find the inverse kinematics of the final destination point, that is point B, and you identify the corresponding joint variables joint variables theta 3, theta 2, and theta 1. And what you try to do is you say that, okay, this was theta 1 for point A, and this was theta 1 for point B. Now you are going to do a linear interpolation of angles, and that is how you do it in Cartesian space description. So in case of Cartesian space description, you have been given the control on the final destination. You say that this where the end effector destination is what has been provided, and the end effector locations are what are being provided, and you are to figure out the joint variables by yourself. In case of joint space description, you make use of the joint variables that they have been asked to move from point A from theta 1 from one angle theta 30 degree to maybe theta 1 to the final angle being 75 degree or something like that. But the point there is you don't have a good control of the end effector location, right? So there are places where, in case if you want your say all you need is so you have a pen attached to your end effector, and you are asking, all you want is the end effector to draw a circle. So if you just make the revolute joint um, uh, the revolute joint which is parallel to the axis of the circle move from 0 to 360 degree, then that is the only thing. So that then you give the input in joint space saying that, hey, this theta 3 move from 0 to 360 degree, I get a circle, right? Now if you are saying that, oh, I need the end effector or the pen at the end effector to draw a point, draw the alphabet A, then you have to specify the first starting point of A, the end point of A, and also the intermittent points. So when it comes to the intermittent points, that is where we do the Cartesian space or the trajectory planning. But let's first try and see a few examples of how we go about the joint angle, uh, the 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 joint space description. So here is a similar case where I was mentioning that you have an RR manipulator. Both have their own individual degrees of freedom, which revolves with an angle alpha, and then the other one with the link 2, which revolves at an angle beta with respect to link 1. And you have been asked to go from point A to point B. Now, when you have to plan from point A to point B, you could always see that, hey, I have the maximum rate of motion, which is which can it can move 10 degrees per second, and that is the characteristic of the motor which is used to create that revolute joint. And if we were to utilize its maximum rate, then you see that your link 1 would reach the point in the first 3 steps, and then you only wait for link 2 to reach point B until the 6th step. But now you see that the path is irregular and the distance traveled by the robot ends are not uniform. This is one way of going about it, which is not wrong, but you can also think of like, okay, what if I try it to uniformly divide the angle variation to reach from point A to point B between theta 1 and theta 2. So what you do is you try to get the range from point A to point B. What is the corresponding range of angle that your alpha needs to make, what is the range of angle that the beta needs to make, and you try to divide them with equal number of divisions. And here, of course, there is um, no constraint provided that you have to make use of 10 degrees per second. You have been given the maximum as the 10 degrees per second, but you may not necessarily use the entire 10 degrees in 1 second. So here you try to divide it. You can plan to divide it uniformly between the 2 points. Now, uh, think of it like this. If you were to make this in a division of equal points, the motion seems to be even. They both the joints, they would move at they will move together, but probably at different speeds. But you would see that you have from point 1 to point 2, you will go and then you stop, and then you will again go from 2 to 3, that you will have to go accelerate and then decelerate and then stop. 3 to 4, go ahead and again stop. Now, why can't we make it a little bit um, more convenient, where you want the point, not convenient, but more something that we would require in real world, where you say um, point A to point B needs to be traveled in a straight line. So you're looking for solutions which will get you the path between point A and B in a straight line. If you see the previous ones, it gets you from point A to point B, but it has no control over the path it is taking in between. Even the one before, you are only giving the joint descriptions here to move at 10 degrees per second, but what uh, the additional constraint that we try to do is We are trying to see if we can make the motion from A to B in a straight line using the same manipulator. So in this, when you try to do this and the inverse kinematics, assuming that you know the locations at point 1, point 2, point 3, point 4, and point 5, and point 6 in the two-dimensional space, that is x and y coordinate values, you could easily do the angle, the corresponding angle values of alpha and beta using inverse kinematics. And that is what you see here, that how in case if you have to do a straight line, that the different values that would take place by equally dividing the straight line, uh, the joint variables are going to follow. Now, when you do this, you kind of realize that the joint variables are not uniformly changing. Um, and we can think of this in different applications. So, for example, as I mentioned earlier, if you want to make your end effector like a pen, like use like a pen on an ink pad or something like that, and you want to make it draw on the pen, draw on the surface, you may need things like this where it needs to move in straight line. But there are applications where if you were to do a pick and place manipulator, if it is just the circular aspect which it is moving, say something more like um, uh, what was mentioned in the comment, like something like articulation of a finger or hand motion, it is something that is more closer to the space that is being consumed by our fingers or our hand motions in this particular fashion. So depending on the application, you decide the trajectory for your robot, and you try to have that incorporated when you try to include the constraints. So what we are discussing here is that if we were to do this, something like applications where you want, say you're using a robot to weld a joint, weld two pieces of plate together, then you want your welding tip to transverse in a straight line along the weld joint. Now, for example, if you have to do the same thing along a circular pipe, then what you need is more like a revolute joint. You have, as I mentioned earlier, you give an angle variation, and then your weld joint actually traverses along the circle, right, along the path. But if you were to join two plates, then you need something like this, which is moving along the straight line. So if you were to do the path of, so so as you could imagine that the joint space the joint space technique that we were shown in the first two slides seems to be fairly convenient for implementation in robotic control. You are just asking the robot to move its joint variables in a particular fashion, and you don't really worry much about the end effector location. But when it comes to end effector location to go in a particular path, what you realize is you need to run inverse kinematics in real time to check that if it is following the inverse kinematics, or if it is following the same points in uh, the trajectory path that you have decided the end effector to move. So when we try to do this, like say to go through a particular path, there are a few aspects of it that you may want your uh, end effector to go to a particular point and stop. So say If it has to just go from A to B and stop, then you could just mention the two positions, identify the inverse kinematics, and then be there. Like, I mean, then give the corresponding angles to the robot to move your theta 1 degrees and theta 2 degrees, and then it moves from A to B and then it stops. Now, say you want to go to from A to C via B, um, you want your manipulator end effector probably just to touch B, or maybe it just wants to go via B to avoid an obstacle in between. There are two cases. So in case of a condition where you have an obstacle in between, it is not as much as to touch the point B, but you're probably giving a location B so that it reaches A to C safely without uh, dropping anything in between, or without striking any obstacle in between. So and this can be considered as not just an obstacle which is external in the environment, but sometimes it is the manipulator itself when it has got like 6 links or 9 links or 10 links, and you ask it to go from A to C, it may wind itself within the links, and it kind of gives you a singularity in between. So to avoid such cases, sometimes we give the manipulator that, hey, you know what, like avoid going through the straight line here, but we want you to go from A to C, but through another path B. Now, if in this case, the final destination is C, and you want the manipulator just to avoid an obstacle, then what you want to do is you want the manipulator not to give like a you want probably the end effector to do a blend. So when I say a blend, it is like it is making use of a B as a point as a via point, or B prime as a via point, where you try to make the movement smooth in that intermediate point, so that it doesn't stop and it doesn't have to restart, and it doesn't give you a jerky motion unnecessarily. But if that is something that you want, say for example, you have a tool which you want to collect something from A, go to B, drop one part of it, then go to C, drop the remaining part of it, then sure, you would like to have from point A, go to B, stop there, drop it, then continue to C, drop the rest of it. But if it is just for the sake of avoiding obstacles, or for the sake of avoiding singularities within the operation, then you would ask the manipulator to do a smooth transition. Now, when you try to do the smoothing, you can smooth it to a larger extent, so which we call it blends. So we can take a curve path with a higher radius of curvature, or you can do like a path with a lower radius of curvature. It depends on the acceleration velocity that you would like to maintain, and then we will just talk about that in a matter of few slides. But just giving you an intuition as to these method of blends are also utilized if you want to avoid jerky motions and loss of energy. At the same time, as I mentioned earlier, say you would really want your end effector to go through the point B, and at the same time you also want it smooth, then what you do is we add two more extra via points, that is D and E. My mistake, this is E actually. So we add two extra points D and E in our path, and say that, hey, you know what, you take a blend here at E and then go through point B, then take another blend at D and go to point C. So remember the case where I was saying that if you want your manipulator to drop something at B and then go to C, but You want your manipulator to probably take a smooth curve or like avoid another obstacle here, but it needs to necessarily reach point B. Similarly, there is another obstacle between B and C, but it needs to necessarily reach C. Then you can use multiple waypoints to add blends and make your motion smooth and attain the same points. All right. So we will get to how we attain that in a matter of few minutes. Um, and one way of doing that is having a good control of your joint angle variations. So when you say the joint angle variations, um, you not just control the two locations. As I mentioned, it is not like just giving the two destinations, but you give your joint angle a time dependent aspect of it, like how fast, how slow, can you change the angle, how soon can you reach the point, and aspects like that, for which we add um, the aspect of polynomial planning in case of the joint variables. So when you say a joint variable theta 1 or theta 2, you can make it uh, go in a linear fashion, or you can make it so it will be like, say theta 1 is 0, or theta 1 was 30 degree. So say in this case your theta 1 was um, 30 degrees, and then theta 2 is like 60 degrees. You would like to go linearly, that is from A to B. You give the position and then the velocity. It is going to be a straight velocity, and then it keeps increasing, or you can give a constant velocity. So you can give those paths, but if you want a better control as to have a smooth blend, then you need control over not just the position, but also need control over the velocity and acceleration. So if you were to do velocity and acceleration, you could think of that your joint variable theta as dependent of time t, and if you have theta, say your angular position, you would find your angular velocity by just doing a different first derivative, right? Similarly, if you want to do an angular acceleration, you do the second derivative. And if you want the time component of the second derivative to control, you need a third order polynomial, which lets you, so if there is no third order polynomial, what happens is, say there is no C3 aspect to it, then after theta and theta dot, you will not have any time variable. You will have a constant acceleration for theta double dot, which is not time varying. So you can't specify that, hey, the acceleration should be varying so and so with respect to time. So like it should not, it should be linearly increasing with respect to time, or it should be linearly decreasing with respect to time. If there is no third order polynomial, there is no control over acceleration. Similar thing goes with velocity. If you don't have a second order polynomial, then you don't have any control over the velocity. And definitely if you need a control over position with respect to time, then you will definitely need uh, the first order polynomial, that is c1 times t. So if you guys are wondering why third order, why not first order, second order, or third first order or second order, the reason for that is to have a time dependency of acceleration, or if we have to control the acceleration over the period of time, then we would like to have the joint variable as a function of third order polynomial dependent on time. Okay. Now, when you have such a third order polynomial, it comes back to your algebra and the algebraic equations and how you solve in linear algebra. Given the initial conditions, you have the constraints, and that depends on your initial angle ti, the initial angle theta I at time instant, or the initial time ti, and it has to reach to an angle of theta f after the time has reached tf. The corresponding velocities can be zero, may not be zero. It can be something that you wish to add, or there will be correspondingly acceleration aspect to it, which you would do that. um, and you would essentially use differentiation or identify the first derivative and need be a second derivative, substitute the initial and final conditions corresponding to um, your velocity and acceleration, position, velocity and acceleration, which gives you the values for all these coefficients: 0, c1, C0, C1, C2, and C3. And that is how we try to identify if there is a linear function of joint variable, we want to add a blend, how to add a blend to the joint variable itself. So to give you an example to make it more clear, say you have six axes, like you would desire the first, just an example to say that the first joint of a six axis robot, you wanted to go from an initial angle of 30 degrees to a final angle of 75 degrees in a matter of 5 seconds, right? Now, you want to know that, okay, in the matter of 5 seconds, if it is needs to reach from theta I of 30 degrees to an angle of theta f of 75 degrees, assuming your ti equals to 0 and tf equals to 5 seconds, using a third order polynomial, calculate the joint angles uh, at 1 second, 2 second, 3 second, and 4 second. Here, what we do is that we have the polynomial, we identify the initial conditions, try to identify some of the constants or the coefficients, and we apply later to more. So here you can see that you have four unknowns, and giving the four constraints, you would get the solution or the answer to these four constants. And what we have done here is that we have tried to identify at different time instances how is your joint variable 1 varying, or it needs to vary if it has to reach um, the angle 75 with the given constraint, where the initial velocity is 0, the final velocity also we are mentioning as 0. But if we were to do a final velocity as a different value, maybe something like 5 degrees per second, then you may get a different value for the intermediate points, right? So another example as to uh, doing this is, if you are given the coefficients, you could very well find the profile of how your joint position, joint velocity, and joint acceleration is varying with respect to time. So what you see here is essentially just the differentiation of each the derivative of this expression, the first derivative and the second derivative, which is getting you the answer. um, okay, just going back to example one. And I will be sharing these slides. I will be uploading them to the Canvas, the class too. But this is just to give you an idea as to how your angles are varying at different time instances for a parabol or like a third order polynomial variation. So you may, like when we did in the when we saw in the earlier image where it was moving from alpha, and when we were moving alpha and beta, you had something like a fixed rate, or like you were incrementing in like 4 degrees or like 5 degrees or something like an even number. But when you do a polynomial fit, you may not get such even clear numbers, but you would have your system moving in a smoother variation with respect to time. Now, just wanted to give you an idea that you could do the same thing with not just third order, but a fifth order polynomial. uh, the idea of doing fifth order polynomial is situations where you need it fine even more smoother or more complicated motion. Then you use a fifth order, which is quite rare. Most of the applications limited by with the third order polynomial, but there are certain applications where not just acceleration, but there is jerk element also uh, considered in case of trajectory planning. Uh, do any of you guys know what jerk is? How do you, I mean, how do you quantify that mathematically? Exactly. So jerk is actually the derivative of acceleration. Okay, it's good that a lot of you guys know this. So jerk is actually a rate of change of acceleration. So we just don't need just the acceleration, but also when we need to control the rate of change of acceleration, if you want to make even the acceleration smoother, then you go one step higher and evaluate jerk, and you want to have control over jerk. There are few, as I mentioned, there are very few applications. If there are some some aspects where, say, in the physical world, if you have some components which is more dependent on magnetic levitation, some to some extent in semiconductor manufacturing, to some extent in uh, the space robotics and things like that, where like jerk is a big deal. You would use fifth order polynomial and have a better control over the acceleration with the initial and final conditions of acceleration, how acceleration also needs to vary with respect to time. If you want to do a quadratic variation of acceleration, then you go all the way to the level of jerk. But for the purposes of this class and many of your real world applications that you see, most of them use the third order polynomial. And as I mentioned, it's just to give you an idea and not something to uh, get you involved with the math or the mathematics behind it uh, to a large extent. So let's consider how you want to do a linear segment with parabolic blend. So when I say a linear segment with parabolic blend, you are thinking of how your velocity, or not the velocity, but how your position from, that is your manipulator, is moving from an angle theta I, or the manipulator, or say link, a specific link 1 is moving from theta I to theta F. And you are not just saying right now that, okay, just move from theta I to theta F, but you are now interested in knowing how it is moving from theta I to theta F. If it is something that I want to do, just not a straight line, but not just a constant velocity, but I want it to like slowly catch up to velocity, and then it reaches a constant velocity, and then ramp down to the velocity 0, so that the other components are not affected. So in such a case, what you do is you try to define the blend and you want to know how to until what point in time will the blend be effective. So so say if it is moving from theta I to theta F, you're planning to make your manipulator move from theta I to an angle value at A, um, and that angle value at A, once it reaches that, then I'm going to make it go on a constant velocity until it reaches a point B, and then it is going, B is closer to the target, so I'm going to make it slowly attain theta F, where you try to reduce the velocity. So when you try to see a position curve and you want to identify how the velocity profile is, this is something that you guys have learned back in your kinematics. You would essentially look for the derivative. The derivative is essentially the slope of the curve that it is described in the position time graph. So if you look at the slope here, the slope would be flat, which would be 0, and you see that the slope is slowly increasing at a point until a point A. So you can see that you could probably visualize in your mind that the velocity is slowly ramping up once it reaches the point A until the point B. Your velocity or the slope of this graph is consistently same, which means that after a point A, your velocity profile is going constant. It is not 0, it is constant. And from point B to reaching theta F, you have the slope slowly going back to 0. So at this point, the slope seems to be around 0. But as you can see that the slope from this point is going slowly going down to 0. So when you look at your velocity profile, it's going to be like something like going up and then constant until point B and then going down. So let's see uh, how that varies. Like this is pretty much the velocity profile and the acceleration profile uh, for the linear segment with blend that we just talked about. So now when it comes to blend, you can decide as to, if you know that t0 is your initial time and it takes tf seconds to reach the theta f value, you can make it like a split saying that, you know what, I'm gonna do the first 1/3 of the time and the last 1/3 of the time in blending, and the in between 1/3 of the time I'm gonna do the linear velocity. So then you have the time values, that is TB, and what is going to be TF minus TB value in your hand, which you can use for those equations. And you can play with the blend accordingly. So if you decide like, oh no, I'm going to do only 1/5, not 1/3, I don't want to take so much time in just blending, so I would be like, I would make the motions more fast and quicker, and I'm going to do the blend in like 1/5 of the initial time and also 1/5 in the end time. The remaining 3/5 of the time I'm going to do a linear velocity, which is going to be pretty much in a straight profile and maybe at a higher value um, that that I would like to attain. So uh, what you could do is you could also do the other way, where you are like, I would like to slowly blend it until half time, which you see here like th, which is essentially the half time. Then at that time you count for the intermediate point where theta h, that is going to be the half value of between theta f and theta 0, and you consider the time, a corresponding time, and you will be like, you know what, I'm going to blend all the way until th in this fashion, and then I'm going to blend all the way until from th to tf in this fashion, which is not very ideal, but you could incorporate blends as much as until the half time is what the point I wanted to make here. is like when you try to do a blend from start to stop, you need to consider the blend only until the half time, because it needs to accelerate and it also needs to decelerate to stop. Now, when you try to evaluate the same using the velocity and acceleration profile, you see that uh, you would you would spend, as you can see when you go to acceleration plot, you see that how much time is it spending in zero acceleration, and how much time is it spending um, in the high value of acceleration or low value of acceleration. Now, if you remember, um, and I'm not sure if you guys have come to this part yet, but if you go to when you guys learn Lagrangian dynamics, what you would see is the Lagrangian dynamics is giving you expressions for the joint variable theta double dot, and giving you dynamical equations in terms of theta double dot. And the reason for that is it is directly equating to the torque required by the joint for making the motions happen. And what you see is if you have more time spent in acceleration, your torque, you're going to apply torque for a longer period of time, and you are going to probably use more energy in that aspect. But it is also a trade-off that you want to do, like you want to save the energy and then avoid much of acceleration, or you just maintain. If you want to maintain a constant velocity profile, then there is no blend perspective. You just need to go slowly, like maybe the slope is even lower, but you will just go slowly and the velocity is going to be really low. So and you could have your acceleration values going really low to save the torque. But if you want the motion to happen in a particular time, and with the blend, you would see that you are essentially also having your acceleration profile, which you would be maintaining to more period of time in the acceleration perspective, and also in deceleration perspective. So the torque is not just for accelerating, but also for decelerating that you are applying, right? So these are like some of the trade-offs I want to give you a perspective of. And it is not something that I'm saying that this is wrong or that is right, but it is the application. Depending on the application, you may want to think about your method of approach that you would like to take it further. Now, when it comes to, as I mentioned, if it is not the final destination, say like you are moving from theta I to theta F, theta J, if it's not a final destination, but it's just a point that you need to go through, then you could add multiple via points. So these lines, these vertical lines that they show are the multiple via points about which you're going to make a blend. And when you're going to make a blend, you can decide the time which is required for the blend at these points based or you could decide yourself and have the blend considered accordingly. So you could fixate on the blend duration, and you could have the smoother curve, uh, like more smooth, like a long duration blend or like a short duration blend, depending on the application that you would like to utilize, and give the according values of time to determine the uh, velocity and acceleration profiles to evaluate your options, right? So the main idea of parabolic blends here is like you decide on the blend time, and you kind of take it from there. Uh, that is uh, that is how it goes about. Now, that being said, you could use higher order polynomials, as I was mentioning, which is not very common, but I just wanted to let you know that you could do that in case of joint angle variation. Now, in case of space-time trajectories, Cartesian space-time trajectories, it is this itself is again a big thing, because there are there are a lot of research work when it comes to Cartesian. So it is like taking from point A to point B in the Cartesian space. Um, it With respect to joint space, it is only very few limited options. Like I mentioned, third order polynomial, you set a blend. You set if you don't want to set a blend, you do just the constant profiling or the straight to profiling, and then that's it. But if you want to do the blend, then you do a third order polynomial, fifth order polynomial, things like that, and then there is that. But when you come to Cartesian space trajectory, you are specifying 2 points. You would like to there are different methods which claim to be the most ideal method. When And that being said, that is the you can add optimization techniques to it. You can add constraints to it. You can say like this is the best method which is avoiding singularities. This is the best method which is avoiding this is the best method as per energy efficiency. This is the best method with respect to deviations from the path, or with respect to this is optimized solution from reaching from point A to point B. So there are multiple ways it can take you in case of Cartesian space trajectories. But the idea of Cartesian space trajectories in all these boils down to this one thing, that if you want to go from point A to point B, you are going to incorporate, say, point A to point B in a straight line. You will have to give, say, 10 intermediate points, and you will have to necessarily do an inverse kinematics for these 10 intermediate points and also for the final destination. Um, and this ends up being this sometimes brings up the question of, when you do inverse kinematics, there is no one true solution to it. There are multiple solutions to it, and I will show you in a matter of minute how that is shown. So let's see if I have that image here. Okay, so you see the image on the right, where it has suddenly shifted from the left side, the manipulator, the manipulator arms from the left side to the right side. But that is not the only solution that it could attain. It probably could attain the same pattern here too. It could, is what I'm saying. But what happens in case of Cartesian space trajectory is this sometimes singularities which bring up. So for example, this is a clear case where if you ask your manipulator to draw a line from point A to point B, and you say that you need to draw a line which is passing through the manipulator itself, it will just stop. It will say that, hey, I found a singular point, I can't move. And uh, it comes back to the designer or the person who is giving the inputs to verify that not just the initial and the final path, but also the intermediate paths are not following or not creating singularity or a non-feasible solution. When I say non-feasible solution, if you have a manipulator whose arm is say 5 centimeter, and it can draw a circle of 5 centimeter, if you're asking the manipulator to draw with that same arm, with that same location, draw a circle of 2 centimeters, then the manipulator is not going to work. It say that, hey, I can't reach the point of a radius of 2 centimeters, and that is because I found a singular solution. And when it comes to the Cartesian space, it is, as I mentioned, it is not just one single solution. It has multiple solutions. Sometimes there are no solution, which is singularity. There are multiple solutions, which gives rise to the orientation problem. So, for example, if you have this manipulator, if you had it to make your signature on a pad which is facing this way, that is like the facing up, and you give the manipulator the instructions or the path so that it makes the signature, it it if it does the inverse kinematics and try to identify the points and say that, hey, I found few solutions on this end and I'm going to use that, you're not going to get a signature on the top surface, and there may not be even a surface on the below, and which is a clear case of it is having multiple solutions, because when you do uh, the orientation in 3 dimensions and you try to say get a point something which is arc cosine of 0 degrees, or not 0 degrees, arc cosine of a value um, uh, 0, it can be both 90 and 270 degrees. So it is very or cos inverse of 0 can be both um, 90 degrees and 270 degrees. And it is that trigonometric function which is giving you multiple solution, and it is also affecting the orientation. So when you do a Cartesian space trajectory, uh, just let me, oops, ooh, okay, sorry about that. Let me share my screen. Okay. All right. So the Cartesian space trajectory would have the issue where it is having multiple solutions with different orientations for the same point in space, and which gives rise to another subject where you have the orientation control of the manipulators in designing Cartesian trajectories, Cartesian space trajectories. So you give a control of orientation and a control of position both to the manipulator at the same time. But the issue there is it becomes more complicated and computationally to do the inverse kinematics in real time and evaluating the next step in the next time instant. And it keeps continuing the loop for the um, the next point. So there was actually a video that I wanted to show, which is like you guys can look it up in YouTube too, where it is about trajectory planning using MATLAB, where a person, which is hosted by MathWorks, he shows a clear image of 6 degree of freedom or 5-axis degree of freedom manipulator using um, moving through the multiple points using the parabolic blend, and also the Cartesian space trajectory, um, both of them. So it's a really cool video. If you guys get some time, you should check it out, and it will give you much more intuition and much more perspective in a three-dimensional world, um, how it works. But as I mentioned, this was just to give you a very brief overview of how trajectory planning goes about it. I mean, goes about in serial manipulators, and to some extent, you use this for UAV systems, quadcopter control, and things like that. where the trajectories are planned in um, three dimensions or the 3D space, but at the same time, um, that also needs an orientation control for pitch, yaw, and roll, so that the quadcopter is moving in a stable fashion. Uh, that's all I had for today as a lecture. But is there any questions, concerns, or anything that you would like to um, know more about, or the calculation part? Okay, is so let me go back to the calculation part. So these examples are, so as I mentioned, it is about the joint space, how you want the how you want the joint space or the joint variable moving, which can give you a good control over velocity and acceleration. So what I mean to say here is, so for example, you have this example where you want to move your angle from theta degrees to 75 degrees, right? And what I'm giving here as the constraints are the initial position is going to be theta 0. So when that is time equals to 0, you substitute the time t values as 0, and what you see is all these part goes to 0. And the initial at initial time t equals to 0, you have your value as 30 degrees, right? And I am also saying that the initial velocity at that point is going to be 0, which because that is going to be the starting point. I mean, I'm just going to start the manipulator right off of that point. So when the velocity, if I'm that is my starting point from the manipulator for anything, then I would make a derivative of this particular I will take a derivative of this particular expression, which gives me something like this. So the derivative of this expression is c1 times 2 times 2t 2 c2t and 3 times c3 times t square. This is going to be the first derivative, and this is the same expression into which I substitute t equals to 0. So if I do t equals to 0, this expression goes to 0, this expression goes to 0. The only thing left out is C1. And that is exactly what I have written here. So the theta dot at t equals to 0 is C1. And I'm giving the constraint that initially the velocity of that joint is going to be 0, is something that I am giving it as a constraint. It is not given in the problem, but I'm giving it as a constraint that the initial velocity is 0, right? Now, I also got that at the end of 5 seconds, the angle is going to be 75 degrees. So I know that this theta f, the theta at tf equals to 5 needs to take a value of 75. So that is what I have done here. When the time is 5 seconds, from 0 to 5 seconds, it needs to move to an angle value of 75. And that is what it did here. From tf equals to 5, the angle value is supposed to be 75. And then I am substituting the C0 value that I already got as 30 over here. I am substituting the C1 value as 0 that I already got here. That is substituted here, 0 times t. Now C2 and C3 I am yet to find, but I know that at t equals to 5 seconds, the angle value should be 75. And that is what I have substituted here. T equals to 5 makes it 5 square. Here it becomes 5 cube. The corresponding value becomes 75. Now, this is one equation that just simplifying this gives me in this form, that is 9 by 5 equals to C2 plus 5 C3. This is one equation that I get from here. Now I'm also adding another constraint saying the velocity like I did for the initial point. Also for the final point, I want it to stop because here in this problem, it just says that it is only discussing only from to the final angle as 75 degrees. So assuming that after 75 degree, my manipulator is not planning to move anywhere, I'm just gonna give it that, okay, let's make it stop at the end of 5 seconds. So when it is going to end or stop at the end of 5 seconds, then I can substitute my theta dot value. That is exactly what I got here, the theta dot expression. That is C1 plus 2 C2t plus 3 C3 t square at the end of 5 seconds. I can say that it is going to be zero, right? So that is what I've substituted as zero. That is the velocity value. And I have substituted the values of C1, that was 0 already, that I got as C1 as 0, and then C2 times 2t, and C3 times 3 times t square is what I have substituted here. Simplifying this equation results in this particular form. So now you have two equations, two variables, that is C2 and C3. When you solve for C2 and C3, you get these constants using these two equations. All right. And using these two equations, you solve for C2, you solve for C3. Now you have all the constants determined from this expression. You have C0, that is year 30. You have C1, which is coming out from this expression, 0. You have C2, which is coming here as 27 by 5. And you have C3, which is negative 54 divided by, actually, this is not 45. I think this is, uh, I think that is 75. I think that's a mistake. Should be 75. Okay. I think I should edit that as 75. Um, okay. So when you go to theta dot, so theta dot is actually the final velocity that I am saying. So for example, um, let's see, let's go to the velocity profile to give you an idea. Okay, so you have your theta f over here and theta 0. This is the graph that we were trying to or actually with the blend we are trying to do. And what I'm saying is at theta f, the velocity, that is like the the manipulator is coming complete, coming to a complete stop. So I am assuming, or I'm saying that that is the final position, and the manipulator is stopping, or the link is stopping at that point. So the theta dot at that point is tending to be 0. So for example, if you consider here, your velocity at the end point is 0, right? Similarly, you have the velocity at this endpoint, that is at the final angle value is 0. So the same way I am substituting the theta dot, oops, not this one. I'm substituting the theta dot at the end of 5 seconds as 0. I'm not talking about any velocity intermittently. I'm just talking about the one initially at point time t equals to 0, and to the end, that is after 5 seconds, where the manipulator has reached 75 degrees and it is stopping, right? So at that point, you have the theta dot at 5 seconds, which is equals to 0. Now, um, what I can do is I'm trying to add here. Um, okay. Cool. So what I have done here is I just tried to use, probably need this one too. Just, um, so this one is C1. this one is t, and this one is t squared, right? Yeah, and that's what I have substituted there. These slides are not there on Canvas yet, but I will be uploading them right after this class is over. I guess I'm not sure if I have the access to that yet, but if not, I will have to ask Dr. Edgar to upload it for me. So it may take a day or two to get it on the Canvas. So uh, just don't want to commit to it. So the velocity and acceleration in these aspects are with respect to joint variables. So they are degrees per second, yes. So being the angle variation, that is theta, it would be degrees per second velocity, acceleration would be degree per second square. And the position is just with the joint space considering the revolute joint degrees. I think there was one more question which I missed out, I guess. Um, for the MATLAB video, Alexis, are you still there? Okay. Okay, the MATLAB video, I can just give you the link. No, yeah, this is the MATLAB link I have pasted on. I was talking about, and yeah, awesome. So yeah, if there are no other questions, I think I ran a little over time, but that is all that I had for today. I'm gonna pause the recording. Oh, stop share, stop recording.